Hi everyone, welcome to Project Pascal, and today my name is Chen Hao and I'm going to cover Kinematics 1. So here's an overview of the topics we'll cover today. We'll start by talking about functions and calculus, how to differentiate functions, how to integrate functions. Then I'll apply calculus that we've learned to derive the Suvat kinematics equations, after which we'll start talking about three-dimensional motion using the concept of vectors, and lastly we'll apply what we've learned to analyze projectile motion. So without further ado, let's begin. So what do we use functions for in physics? We use functions to describe motion, and we use functions to describe things like potentials. Now I have a lot of examples listed over here, but I'm not going to go through all of them in detail, and if you want to see detailed descriptions of all these functions, feel free to check out the in-depth lecture I have over here. But because we're going to cover a huge range of subtopics in this Kinematics 1 lecture, I'm just going to cover the parts that are more relevant to kinematics. So for kinematics, we'll mainly be using functions from R to R, as well as functions from R to R3. So what does that mean? So functions from R to R take in a real number and output a real number. So an example of a function from R to R is the function x of t. So in this case, the function x of t takes in an input t representing time that is elapsed, and it outputs the x coordinate of a particle. So for example, if the function x of t is given by 5 sine 2t, then if I tell you that the time t right now is 2 seconds, then you can substitute this t equals to 2 into the function x of t, get that the particle's location or the particle's x coordinate at 2 seconds is equals to 5 sine 4, which is a numerical value. So functions allow us to describe the motion of a particle throughout time by specifying for each time t how to calculate the particle's position. But this is just for 1D motion. Right? In 3 dimensions, we need to describe the particle's location using 3 coordinates. If you play Minecraft, you'll know that usually when you give your friend your coordinates, you give them 3 numbers. So in those cases, we'll be talking about functions from R to R3. This R3 on the right side over here just means 3 numbers put together. We can also think of this R3 as a vector, but more on that later. So for example, how we can specify such a function is we provide the x, y, and z coordinates as functions of time. So perhaps x of t is 5 sine 2t, y of t maybe is half t squared, and maybe z of t is just t. So this way we have specified the motion of the particle throughout time in 3-dimensional space. Now when we talk about functions, we aren't just limited to functions describing the position of a particle. We can also talk about functions describing the velocity of a particle. So for example, if I say that the x component of velocity of a particle as a function of time is 10 cosine 2t, that means that at time t equals to 1, we substitute in t equals to 1 into the velocity function. The velocity of x at time t equals to 1 is equals to 10 cosine 2. And this numerical value is how fast the particle's x coordinate is changing. The concept of velocity is going to be covered in greater detail later when I talk about calculus and differentiation. We'll actually say that the x component of velocity is the derivative of the x coordinate with respect to time, but more on what this means later. And of course, there's other examples such as acceleration. Acceleration can also be described as a function of time, and in general, the concept of functions also extends to a lot of other things. But these 3 functions will be our concern for kinematics 1. So with that out of the way, that's all we need to talk about functions for kinematics. Once again, if you want a more in-depth lecture on the other applications of functions such as functions describing gravitational potential energy or functions describing electrostatic force, right, vector fields. If you want an in-depth explanation of those, feel free to check out this link at the top of each subsection. So with that, we're ready to talk about calculus. So the first concept we're going to talk about is differentiation. I'm sure you guys are probably familiar with how to take the gradient of a linear graph. If I draw a graph over here and I say that the graph is described by y equals to 2x plus 3, you would calculate that the gradient of the graph is, and what that means is that if I start on a point over here, I move 1 unit to the right, then you move up by 2 units. In other words, this is the rise over run. So given a linear graph, you can calculate the gradient of the linear graph by picking any 2 points and using this formula. Now this works for graphs which are straight lines. But what if we have a graph that is curvy? So for example, what if we have a graph which is y equals to x squared? Now if I ask you what is the gradient of this graph, you cannot give me just a single number to describe the gradient of it, because the gradient of a non-linear graph is defined by drawing a tangent line to the point at the graph. The tangent line means that it just touches 1 point and is just barely kissing the graph. Now we can see that if we pick a different point on the graph, the tangent line will have a different slope, and this means that there isn't a single number that can describe the gradient of y equals to x squared. Instead, for every single point on the graph, for here, for here, for here, for here, for here. For every single point along the graph, for every single x coordinate on the graph, we actually need to specify a real number. And that means if I give you a certain function, let's say y equals to x squared, and I calculate the gradient of that function will actually be another function, which in this case, if we calculate it out, it will be y equals to 2x. Now the question is, how do we find this y equals to 2x function from the y equals to x squared function? How do we perform this operation of taking the gradient? And this is precisely what differentiation is. Differentiation is finding the gradient of a function. So in this case, the algebraic calculations would look something like that. We say that the derivative of a function, which we denote with f prime of x, is equals to the limit as h approaches 0 of this ratio. Now let's understand this ratio a little bit further. If we draw the graph of a function f of x, at some point x naught, the value of the function is going to be f of x naught. At another point, x naught plus h, the value of the function at that point is going to be f of x naught plus h. These are the two quantities that appear in the numerator of the fraction, and we're taking the difference of these two values. That means we're taking the difference in height over here. Now the denominator is just the difference in x coordinate, which means it's the run over here. So the quantity over here is actually just the rise over run between 2 points x naught and x naught plus h. In other words, the quantity in purple over here is actually the gradient of the line that passes through these 2 points. Now what is this limit h over here? This limit h over here, as h approaches 0, it means the limit of this purple quantity, this fraction, as h approaches 0. And what happens when h approaches 0? This quantity over here shrinks to 0. It approaches 0. And the two red lines over here get closer and closer. In other words, the definition of the derivative of a function is actually just the rise over run of 2 points as the 2 points approach closer and closer and closer. And in this case, as the 2 points approach each other, the purple line over here becomes a tangent line. So that's how we define differentiation from first principles. Now if you plug in the function f of x equals to x squared into the following definition and we calculate it out, we'll actually get 2x. I go through the detailed derivation of these steps over here in the lecture here. So that's the basics of differentiation. Now I'd like to emphasize two things. One is the geometrical aspect of differentiation. Geometrically, the derivative of a nonlinear function is the gradient of the tangent line at every point along the function. Now algebraically, how we calculate this derivative is by taking the limit as h approaches 0 of the rise over run. But we don't usually do this for every single function we encounter. Instead, we memorize some rules for differentiation. And now I'm going to talk about the rules. So these are some of the important rules. For example, there is linearity of differentiation, which means that the derivative of the sum of two functions is a sum of the two individual derivatives. I go through some examples in the detailed lecture over there, but in this case I'll skim through and talk about the more important ones. A constant pulls out of the derivative. If I differentiate a polynomial, the exponent drops down and the exponent decreases by 1. For trigonometry, if I differentiate sine, I get cosine, and if I differentiate cosine, I get minus sine. This is going to be useful for simple harmonic motion. For the exponential, the derivative of e to the x is e to the x itself. And for the product rule, the derivative of the product of two functions is given by the following: f dg dx plus g df dx. Now 3 Blue 1 Brown has a great series on understanding these derivative rules, and he has nice animations and things, so I recommend that you check out his series. And lastly, the one that's quite important for physics is the chain rule. We'll see the chain rule appear quite a lot. I cover some examples of the chain rule in my detailed video. Now, how is differentiation useful? Differentiation is used in kinematics, later on when we talk about the Suvat equations. But besides that, we can also use differentiation to find the minimum or maximum of a function. And this concept can be used in questions that they tell you to maximize the range of a projectile, or they tell you to maximize the height of a projectile, or they tell you to maximize or minimize some quantity in some physics Olympiad problem. Sometimes you can frame it in the language of calculus and you can apply differentiation to find the maximum. So for example, if I have the function f of x equals to minus x squared plus 2x minus 1, the graph of the function looks something like that. How do I find the maximum point in this function? Notice that at the maximum point of this function, the gradient is 0. That means we can differentiate this function and set the derivative to equal to 0. And by solving that equation, we'll get the x-coordinate at which the function is maximized. So in this case, the maximum point of this function is at x equals to 1. I can also use a similar procedure to find the minimum of a function. For minimum of a function, the derivative is also 0. But this raises the question, if the derivative is 0 both for minimum and maximum points of a function, how do I find out whether the point I've just calculated is a maximum point or a minimum point? For that, we can perform the second derivative test. which means that I actually take the derivative of this function again. So I differentiate the derivative and I get that f prime prime of x is equals to minus 2. So based on whether the second derivative is negative or positive, we can determine whether the point we have just found just now is a maximum or minimum. Now if the second derivative is 0, such as in the case of f of x equals to x to the 4, then taking the second derivative will actually give you 0, and we have not enough information to conclude whether the point we have calculated is a minimum or a maximum point. Now if I may invite you to try the following exercises, you can pause the video, and I'm just going to quickly write the answers out. Okay, so now the answers to these are going to be 4x cubed plus 2x. The answer to the next one is going to be 5. The answer to the next one is going to be minus 1 over x squared. The next one is 2 cosine 2t. The next one is minus 5e to the minus 5t. And the last one is going to be secant squared x. Now, if you want a detailed derivation of these answers, feel free to check out my in-depth video. Now you can see that differentiation is about following a bunch of rules and applying them diligently. So I encourage you guys to practice more differentiation because you're going to use it in higher levels of physics anyway. So it's good to just learn it ahead of time. Now that I've covered the concept of differentiation, let's talk about integration. So integration is the opposite procedure of differentiation. That means if I give you f of x equals to x squared, and if you calculate the derivative of it to be 2x, then integration is going the other way around, in that I give you the derivative of a function and I want you to recover what is the original function. Given 2x, I want you to find x squared. So this may seem simple for small examples, but it turns out integration of general functions is actually very difficult. Some functions don't even have a closed form for the integral. So you often denote integrals with the integral sign. So you can say the integral of 2x dx is equals to x squared, where this part is what we call the integrand. This dx over here tells us we're integrating with respect to the variable x, and the integral sign tells us we're integrating. Now there's an important point, which is that notice that if I differentiate x squared plus 1, or I differentiate x squared plus 2, or differentiate x squared plus 3, it all gives me 2x. So if I ask you the question of what function, when differentiated, give me 2x, the answer isn't just a single function x squared. The answer is actually a whole family of functions x squared plus c, where c is an arbitrary constant. So when doing things mathematically, you need to specify this plus c over here. If not, your integral is technically wrong. And in physics, this plus c over here usually plays the important role of giving us the initial velocity or the initial position. We'll talk more about this later. So here are some physics examples of integrals. I'll give you a moment to try them out, and I'm going through the answer now. So the integral of 5 dx is going to be 5x plus c, where c is an arbitrary constant. Now the double integral of minus 10, right, is going to be the integral of minus 10t plus c dt, and that's going to evaluate to minus 5t squared plus c plus d, where c and d are arbitrary constants. Now the double integral of minus 10 is used in calculations involving gravitational acceleration. The integral of sine 5t is going to be minus 1 over 5 cosine 5t plus c. One can check that if you differentiate minus 1 over 5 cosine 5t plus c, you get back sine 5t. And lastly, the integral of 1 over x squared is going to be minus 1 over x plus c. The last example is used for the calculation of potential energy for the inverse square law, such as the example of gravitational potential energy or electrostatic potential energy. Now what is integration useful for? Integration is useful for finding the area under a graph. So for example, if I give you some function over here, and this is the x-axis, and I tell you to calculate the area under the graph from this point A to this point B. You can calculate the area of the graph by performing an integral. So if this function we label as f of x, then the area is going to be given by what we call a definite integral from A to B, and we denote that with putting the two A and B at the bottom and the top of this integral sign. Then we write f of x dx. Now suppose that the antiderivative of f of x is big F of x. In other words, if I differentiate the big f of x, I get f of the small f of x. Then in this case, we're going to get big F of x plus c. And what we do with this a and b is we substitute it into the big F of x, and we take the difference between the two. So we're actually going to take f of b minus f of a. Now we can see that when we do such a thing, the plus c essentially cancels out because there's a plus c here and there's a minus c over here. And I'd like to invite you guys to think about what that means in the context of our graph over here. So for example, I have a graph here, big F of x. If I do big F of x plus 1, it's going to give me the orange graph. And if I do f of x minus 1, it's going to be the blue graph. We can see that f of b minus f of a is unchanged by vertical translations of the big f of x graph. But if that's too much, it's okay. Just note that when we do a definite integral, the plus c essentially cancels out. Now one also needs to be careful about the concept of a signed area. If I have a graph that goes under the x-axis, for example this, then the area from this point A to this point B is actually going to be negative. Now in physics, the concept of integration appears in many places. Here are 3 examples. So for example, the energy in a spring is given by the integral from 0 to x of kr with respect to r. And the answer to this is going to be half kx squared. This kr over here represents the force according to Hooke's law. And this half kx squared is the potential energy stored in a spring. And what we have actually done over here by this integral is the work energy theorem. Likewise, similarly, we also perform a similar type of math when we talk about energy in a capacitor. Now, you don't need to know this physical context in order to perform the math. And in fact, I want to emphasize that by understanding the math very well, you are actually separating concerns regarding physics and the math. And complicated concepts in physics, such as the gravitational potential energy, will simply be reduced to some mathematical calculation which you can just perform purely mathematically. And often in physics, you think about physics as the physics aspects and then the math aspect. The separation of concepts make it easier to understand physics as a whole. So energy in a capacitor is going to be given by half q squared over c, and gravitational potential energy is going to be given by minus 1 over r. Now if you want me to go through the detailed derivations over here, please consider this video where I actually go through the detailed derivations of how to perform these integrals. So with that out of the way, let's recap what we've learned so far. We first went through the concept of functions, and we said that functions take in an input, usually is time in the context of kinematics, and it gives you an output, which is usually the coordinates of the particle. Now, if I give you a function, you can perform 2 types of operations on it. You can differentiate it to find the gradient of the function, or you can integrate it to find the area under the graph of that function. Now, differentiation has 2 important aspects. One is the geometrical intuition for it. The geometrical intuition for differentiation is basically finding the gradient of the graph at a certain point by drawing a tangent line to the graph at that point. And the other aspect of it is the algebraic calculations. Algebraic calculations can be derived from the first principles over here. This is a definition. This limit thing over here is a definition of the derivative. But in practice, we don't really apply the limit all the time. In practice, when we want to calculate the derivative of a function, we apply these derivative rules. And lastly, we went through how to use the derivative to find the minimum and maximum of a function. Now, the other concept we talked about is integration. So integration has 2 aspects of it. One is the definite integral and one is the indefinite integral. The definite integral helps you calculate the area under a graph. So for example, if I give you some function, I'll calculate the area under the graph, you can use definite integration. The indefinite integral is merely, symbolically, the antiderivative of a function. So for example, the indefinite integral of 2x dx is equals to x squared plus c. If we take the indefinite integral and substitute in endpoints to the integral, then we can substitute in these 2 endpoints and get 3 squared minus 1 squared equals to 8. And this definite integral, the result of this definite integral is the area under the function 2x from the endpoints x equals to 1 to x equals to 3. So onto the concept of kinematics. If you want to study kinematics, the first thing you need to do is establish a coordinate system. And a coordinate system means we need to specify in some direction in which the coordinate is increasing in. So for example, if I say that my x coordinate increases moving to the right, then for example, this location is x equals to 0. And if I move to the right by 1 unit, I get x equals to 1. If I, on the contrary, specify that the coordinate system is leftward increasing, then if I have some point over here, x equals to 0, and I move to the right by 1 unit, I'm going to get x equals to minus 1. Now, the reason why I'm mentioning this choice in convention you can make is because in some examples, one choice might actually seem better than the other. So I think the typical example would be the example of a pendulum. Pendulum that makes an angle theta. Perhaps you choose x to be rightward increasing. Now the question is, should I choose y to be upward increasing or downward increasing? If I chose y to be upward increasing, then the y coordinate of the pendulum will actually be minus L cosine theta, where L is the length of the string. But you can see that this might be a bit jarring. So in this case, we actually might want to make the choice in which y is downward increasing, and that way we have y equals to L cosine, and this positive quantity seems a lot simpler to work with. So of course you can pick any choice of coordinates you want. You can define any direction to be the increasing direction for the coordinate, but some choices might make your algebra look a bit neater and avoid too many minus signs. Now it's important to mention for 3-dimensional motion, the moment you pick directions for the basis vectors x and y, you need to automatically set the basis vector for z according to the right hand rule, because z is going to be equals to x cross y. More on that in vectors later, but just note that you can pick any direction you want for x. You must pick a perpendicular direction for y, but it's up to you whether you want to choose it to be upward increasing or downward increasing. But the moment you make the choice for these two directions for x and y, you cannot make the choice anymore for z. In this example, z will automatically be fixed to be into the page increasing by the cross product rule. So with that out of the way, the moment you choose directions for increasing directions of x and y and z, you can describe the motion using functions. So if I say x of t describes the x displacement as a function of time, this concept of displacement is similar to distance but is sensitive to a sign. So what I mean by this is, if I start over here and I move 1 meter to the right, my displacement is 1 meter and my distance traveled is also 1 meter, assuming I've chosen rightward to be increasing. If I then move from the right to the left by 1 meter, my displacement would be -1, but my distance would still be +1. Now this concept of displacement is important because if I move to the right by 1 meter and I move left immediately by 1 meter, my total displacement is 0 meter, right? Because moving left by 1 meter undid my moving to the right. But my distance traveled is actually 2 meters. So displacement is sensitive to the direction you travel in. Moving right versus moving left will differ by a minus sign. So this x of t represents the displacement from some origin as a function of time. So in other words, this x of t describes how you move along this one-dimensional line with respect to time. How your displacement with respect to some origin changes over time. Now, our goal in physics is to understand how the displacement of an object changes over time. And the reason is because if we know where an object is at every single point in time, we have essentially solved for everything we know about the object's behavior. Right? If we know the functions x of t, y of t, and z of t, we know exactly how the object moves. Now, the information most physics Olympiad problems will give you is quantities like forces acting on the object, or the object's velocity, or the object's acceleration. And it's our job to convert these pieces of information into the position over time. Now, the first set of equations we learn for kinematics is known as the Szilard equations. And in this case, S is the displacement, U is the initial velocity, V is the final velocity, A is the acceleration, and for Szilard equations to apply, we must assume that acceleration is constant over time, and t is the duration for the motion. Now, there are 5 equations describing how all these 5 variables relate to each other, and you can see that for every one of them, we have 4 variables appearing in the equation. So for example, in the first one, we have variables v, u, a, and t. Now, because we have one equation relating these 4 variables, that means that if we know any 3 of them, for example, if I know v, a, and t, then I can find u. Or for example, if we look at the 4th equation over here, if I know v, u, and t, then I can find s. So out of these 5 equations, if we know any 3 variables, we can find the other 2 that are unknown. Now, how do we arrive at the Szilard equations? For that, we can use calculus. So s is the particle's displacement over time. In other words, it's the particle's position as a function of time. If I give you a function s of t, you can tell me exactly where the particle's location is at every single point in time. You know the entire history of the particle's trajectory. Now, if I ask you, how fast is this particle moving at every point in time? The answer is that the velocity is the rate of change of the displacement. Now, do note that just like displacement is sensitive to the direction and the sign, velocity is also sensitive to direction. So for example, if we set rightward to be the direction of increasing x coordinate, then if the particle is moving to the right, the velocity is positive. And if the particle is moving to the left, then the velocity is negative. Now, how we encode this idea of rate of change of displacement is by using the derivative. We differentiate with respect to time, the function describing the displacement of the particle. So mathematically, velocity is the derivative of displacement. Now, next up, we have that acceleration is the rate of change of velocity with respect to time. So the acceleration is the derivative of velocity. And that also means that acceleration is a double derivative of displacement. Now, to derive the Szilard equations, we are concerned with scenarios where the acceleration is constant over time, meaning that acceleration is a function of time. It's just some constant number a0. And this a0 could be, let's say, 5, or it could be 6, or it could be 9.81. In cases where the acceleration is constant, if I give you the constant a0, you can integrate once to find the velocity as a function of time. And that's given by equations 1.8. And if you know the velocity over time, you can integrate it again to find the displacement over time. And that's given by equation 1.19. Now with that, we've derived equations 1 and 2 from the Szilard equations. It suffices to make a few rearrangements and derive the other 3 from the first 2. However, later, I'll share a very interesting derivation for the third Szilard equation and its relations to the work energy theorem. Now geometrically, the Szilard equations can be thought of as the area of a trapezium. Because we know that velocity is the derivative of displacement with respect to time, if we integrate both sides, we can see that displacement as a function of time is the integral of velocity with respect to time. Now if we plug in endpoints for this integral, Ta and Tb, we'll get that the difference in displacement between 2 times t is equals to the definite integral from Ta to Tb of the velocity time graph. Now what does this look like? Geometrically, if I have 2 times Ta and this is the velocity time graph, the change in displacement delta s, which is the left hand side over here, is simply the area under the graph. Now for the case of Szilard equations, we are concerned with constant acceleration motion, which means that the velocity time graph is linear, which means that it's straight. So our graph looks something like that. Ta and Tb, this is the v with respect to time, this is time, and hence the displacement is just the area under the trapezium, the gradient is just the acceleration a0, and the initial and the final velocity is just the height of the vt graph at times Ta and Tb. With this, actually, this is also another way to geometrically derive the Szilard equations. And in fact, the vt graph, the velocity time graph, is a very good way of thinking of most kinematics questions. Now I'm going to go through one such question because I feel like it's a very good illustration of the concept of a velocity time graph and the area of a trapezium, and I'm going to leave the other questions as homework for you guys. So for this question, an object is traveling in a straight path exhibiting constant acceleration a with the initial velocity of 2 meters per second. It traversed 4.5 meters in the third second from t2 to t3, and its acceleration we need to find. So in this case, we could use the Szilard equations, but I think it's a lot simpler if we just draw the velocity time graph. So let's draw the velocity time graph. So the object starts at 2 meters per second and it travels at a constant acceleration a. That just means that the gradient of this graph is equals to a. It traversed 4.5 meters in the third second, which means that from t2 to t3, the area is 4.5. Now we know that after 2 seconds, the velocity here is going to be 2 plus 2a. And after 3 seconds, the velocity is going to be 2 plus 3a. So that gives us the two heights of the trapezium. The base is just 1 second over here. So the area of the trapezium is half times the sum of the two heights. So it's 5a plus 4. And we get that the area is 4.5. Now solving for a, we get that a is equals to 1. And that's option B, which is correct. So you can see that by simply drawing the velocity time graph and identifying the correct area and the gradient, we can very easily find the answer without thinking about the 5 Szilard equations. So this is my preferred way of approaching most kinematics questions, by drawing the velocity time graph, and I recommend you try the same too. I have a few other examples over here, but most of them are simple enough that I don't think they're worth covering in this lesson in great detail. You can always watch the lectures over here for the detailed explanation for each question. So before we end up the lesson, I just want to mention an extra little interesting concept, which is that the third Szilard equation, right, v squared equals u squared plus 2as, is actually very related to the work energy theorem. So I go through the derivation in this video in greater detail, but roughly speaking, if we look at the idea that the acceleration is the second derivative of displacement with respect to time, then we know that if we integrate both sides with respect to time, we get the Szilard equation. But if we integrate both sides with respect to displacement, then we're actually going to get v squared equals u squared plus 2as. So this is interesting because its connection with the work energy theorem is that the work energy theorem tells you that the integral of force with respect to distance is equals to the change in kinetic energy. And we know that kinetic energy has a half mv squared, right? We know there's a v squared over here. So in other words, this v squared equals u squared plus 2as equation, if we slap on a 1 over 2 times m, we slap on the factor of half the mass, then essentially that will give us the work energy theorem. Now I don't want to bore you with the details, so you can refer to the video over here if you want to check it out. Now that we've covered fully the one-dimensional kinematics, we're ready to talk about three-dimensional kinematics. And there isn't too much that actually changed. The only difference is that now we're dealing with 3 displacement functions instead of just 1, right? Each displacement function describing the displacement in that direction. If I give you 3 functions describing the x, y, and z coordinates of a particle over time, instead of writing x, y, and z separately, you can package them up into a single thing known as a position vector, and we denote it with a column of numbers like that. Now for vector quantities, we often write an arrow over it, or sometimes you'll see the text bolded. So numerically, a vector is just per a collection of three numbers which we often write vertically like this with a big bracket. But geometrically, a vector can be thought of as an arrow in space, an arrow that has direction and magnitude. So if I give you 2 points in 3D space, you can draw an arrow from one to the other, and that is known as a vector. If we say the vector has components of 1, 2, and 3, right, it means that the vector points 1 unit in the x direction, 2 units in the y direction, and 3 units in the z direction. We can calculate the length of the vector using Pythagoras theorem, and we'll get square root of 1 squared plus 2 squared plus 3 squared, which will give us square root of 14. Now there are a few operations you can do to vectors. One is you can add them. Adding them numerically just corresponds to adding the individual components of the vectors. So for example, x1, y1, z1 plus x2, y2, z2 is just the sum of the components x1 plus x2, y1 plus y2, and z1 plus z2. Numerically, you're just adding each component with each component. The x component add together, y component add together, z component add together. And this makes sense because if you move x1 in the x direction and then you move x2 in the x direction, you move a total of x1 plus x2. So that's how you add vectors numerically. But what is the geometrical interpretation of adding of vectors? The geometrical interpretation is if you add two vectors a and b, you're lining up the tail of the b vector to the head of the a vector. And the composite vector from the tail of a to the head of b is going to be the sum of the two vectors. Now notice that vector addition is commutative, meaning that when you add a and b, or b and a, you get the same vector. And this is true because this a plus b or b plus a forms a parallelogram. And that's it for vector addition. Now vectors can also be scaled. You can multiply a vector with a single real number, and that will scale the length of the vector while keeping the direction the same. So for example, if I have a vector over here, 1, 2, 3, and I multiply the vector by the real number 4, then the vector will be scaled to 4, 8, and 12, and the direction will stay the same, but the length will increase by a factor of 4. Now question, what if you multiply the vector by a negative real number? Then the vector I get is minus 2, minus 4, and minus 6. You see that the direction has flipped. And the reason why vector scaling is defined this way is because if you add 1, 2, and 3, with minus 1, minus 2, and minus 3, you're going to get a 0, 0, 0 vector, which is the vector, if you add them together, it's the vector that has 0 length and just no direction at all. It's just a point. So that's why vector scaling is defined with a negative sign by flipping the direction of the vector, because we want a vector plus the negative of a vector to be equal to the 0 vector. Now length, we've mentioned length before, right? You can use Pythagoras theorem, and now it's time to talk about products of two vectors. Now there are two types of products of two vectors. If I give you two vectors, right, you can multiply them together in two different ways. The first way is known as a dot product. If I give you two vectors, you can calculate, in essence, how similar in direction they are, right? How similar they are. So if I give you two vectors, you can see that these two vectors roughly point in the same direction. But if I give you these two vectors, you can roughly see that the two vectors point in different directions. Now, how you quantify this difference in directions is using the dot product. And numerically, how you calculate the dot product is the dot product eats two vectors and it spits out one real number. The real number is calculated as the sum of the products of the components. So for example, x1, y1, z1, x2, y2, z2 gives me x1, x2 plus y1, y2 plus z1, z2. So for example, if I do 1, 2, 3 dot minus 1, 4, 6, that will give me minus 1 plus 8 plus 18, which totals to 25. Now this is numerically how we calculate the dot product of two vectors. But what's the geometrical interpretation? As I said earlier, the dot product tells you how similar the direction of the two vectors are. And so geometrically, the dot product is actually the product of the lengths of the two vectors multiplied by the cosine of the angle between them. So you can see that this angle, for example, this angle is, let's say, around 45 degrees. And this angle is around 135 degrees. In this case, the dot product of the two vectors over here, a and b, is the length of the two vectors, which are positive quantities, multiplied by cosine 45. And cosine 45, we know, is a positive quantity as well. So the dot product is positive overall, because each of the individual three vectors are positive. But in the second scenario over here, where we have, for example, a and b, the dot product of these two vectors are the product of two lengths, which are once again positive quantities. Right? The two lines over here denotes the length of the vectors, and if we multiply by the cosine of 135 degrees, cosine of 135 is actually a negative quantity. It's less than 0. So if I have a positive times a negative quantity, I'm going to get something that is overall negative. So you can see that first of all, the dot product is positive if the two vectors point in similar directions, and is negative if the two vectors point in roughly different directions. And where's the part where 0? The dot product of two vectors are 0 if the two products are precisely perpendicular, right? The dot product is going to be equal to 0 because a dot b is going to be the length of a times the length of b times cosine of 90 degrees, and cosine of 90 degrees is 0. So what the dot product actually allows you to do is calculate precisely the angle between two vectors, because if I give you two vectors a and b, you can calculate their dot product. You can calculate the lengths of each one of them individually, and then you can take the ratio of those two quantities, right? A dot b over length of a times length of b to calculate the angle theta between the two vectors. So the dot product is useful in physics because we use it to calculate things like work done as well as concept of flux as in electromagnetism. Okay, so that's it for dot product. For the concept of cross product, if I give you two vectors, you can, besides calculating the dot product, you can also calculate the cross product. In this case, the cross product is a different type of product because the dot product takes two vectors and it outputs a single real number, one single real number, right? But the cross product actually takes two vectors and it outputs another vector. And so what is this vector numerically and what is this vector geometrically? Numerically, the cross product uses this slightly convoluted calculation, and basically the x component, you can see the first component, the x component of the cross product of two vectors is the y1 times z2 minus the z1 times the y2. The y component of the cross product is going to be z1 times x2 minus x1 times z2. And lastly, the z component of the cross product is going to be x1 times y2 minus y1 times x2. So how you want to memorize this formula is up to you. There are some methods known as the shoelace formula. You can Google it a bit, and it's ultimately up to you, and practice does help remember this formula. So numerically, the cross product is calculated by what I'll call the shoelace formula. But what is the cross product geometrically? The output of a cross product is a vector, and a vector we know has direction and magnitude, right? It has a direction and a length. So to describe what the cross product is geometrically, I need to tell you the direction of the cross product as well as the length of the cross product. So the direction of the cross product is given by the perpendicular vector to the plane spanned by the two vectors. So may I refer you to this diagram over here? You see that if I have two vectors a and b, they span a plane. You can imagine that there's a plane that these two vectors lie on, this two-dimensional plane that these two vectors span or lie on, and that plane is going to be this infinite plane, and the cross product of these two vectors is going to be perpendicular to this plane. And so now you may be wondering, wait, perpendicular? But there are two perpendicular vectors to a plane, right? Which one do I choose? If I have a plane over here, there are technically two perpendicular vectors. Which one is the direction for the cross product? And the answer to that question is that the direction of the cross product is given by what we call the right hand rule. So if I use my hand over here and I use the pointing finger to be the A vector and the middle finger to be the B vector, and I put them up like this such that the thumb is perpendicular to both the A and the B vector, then this is the direction for A cross B. If I do B cross A, then I need to flip around my hand and you see that it points in the opposite direction. So A cross B is actually minus B cross A, right? This is sometimes what we call anti-commutativity. So now I specified the direction. What is the length? The length of the cross product is actually the area of the parallelogram spanned by the two vectors A and B. So if I have two vectors A and B, and I'll find the length of the cross product, right? I'll draw a parallelogram that these two vectors span, and the area is going to be the length of the cross product. So what is the cross product used for in physics? The cross product is used for many concepts such as torque and angular momentum, or even things like the Lorentz force of the pointing vector. So just like how you can take derivatives of functions, you can also take derivatives of vectors. So derivatives of vectors are just calculated coordinate wise. So if I have the derivative of this vector x, y, and z, I just apply the differentiation to each of the individual component functions. Lastly, the concept of basis vectors. Basis vectors comes in especially useful later on when we talk about rotational motion. And it'll make a lot of more sense when we talk about rotational motion, because in that case we're actually working with different basis vectors. So for now, basis vectors are the vectors with 1 in the individual x, y, and z components. As we know, vectors can be added together and they can be scaled by some number. So if I write x, y, and z as follows, such that it's x times 100 plus y times 010 plus z times 001, then I can call this 1, 0, 0, 0, 1, 0, and 0, 0, 1 vectors as the I, J, and K basis vectors. Sometimes we see them written as x hat or ex, and the collection of these three vectors is called the basis vectors. So this is what we call the Cartesian coordinate basis. In future, in the next lesson, we'll talk about rotational motion, we'll talk about the polar basis vectors. Okay, so that's it for vectors. There are a few questions over here, but honestly, they are not good questions. I just picked them because they appear in the SJPO paper, but I wouldn't, you can try them. I don't think they are very pedagogical, so I'm going to skip over them. Okay, so with that, so now that we've covered three-dimensional motion, we're now ready to talk about projectile motion. But before we talk about projectile motion, I just want to quickly mention the formula F equals ma. This will be covered in greater detail in one of the dynamics lectures, but I just want to quickly mention it so that we know where the acceleration function comes from. So we know that if I give you the acceleration as a function of time, if I give you this function, you can integrate it twice to get the position as a function of time. But in most physical cases, we don't get the acceleration function directly. Instead, we're given how much force is applied to the object as a function of time. So usually we're given the force on the object as a function of time. And basically force and acceleration just differ by a scalar m. So if I give you the force as a function of time, you just need to divide by m to get the acceleration as a function of time. And that's all you need to know for now. So now, let's talk about projectile motion. If I have an object that I throw with speed u at some angle theta with respect to the ground in the xy plane, then the only force acting on the object, assuming negligible air resistance, the only force is going to be the gravitational force mg downwards in the minus y direction. So the F equals ma equation will be given by equation 1.32, where the acceleration vector is the second derivative of the position vector. Now if I compare equation 1.32 component-wise such that 0 is equals to d squared x dt squared m, and minus mg is equals to m d squared y over dt squared, and 0 is equals to m d squared z dt squared. If I integrate both sides with respect to time twice, I'm going to get that the x, y, and z coordinates are given by the three functions over here. Now substituting in ux, uy, and uz equals to u cos u sine theta and 0 respectively, as well as assuming that the initial displacements are 0, meaning that the object starts from the origin, we can arrive at the following expressions for the x, y, and z as a function of time. Namely, we see that x as a function of time is this, and y as a function of time is this. And both of them are function of time, meaning that if I tell you a certain point in time t, you can tell me the x and y coordinates. This is known as a parametric curve. And what a parametric curve is essentially a collection of points. Right? A parametric curve is a collection of points. So if I tell you at t equals to 0, the ball is here. Right? You put one point over there. I tell you at t equals to 1, the object is here. Right? This is x1 and y1. If I tell you t equals to 2, the object is here. Right? That's t equals to 3, the object is here, t equals to 4 is here, 5, 6, 7, 8, 9, 10, 11, 12. Since you know x is a function of time and y is a function of time, if you vary the parameter t, you're going to get that the object traces out this parabolic motion. And that is what we mean by parametric curve. You're varying the parameter t. The time t is a parameter describing this curve. And this is useful if you want to, for instance, answer the question, at this time t, where's the object? At this time t, where's the object? However, it's not so useful if you want to do things like maximize the range of the object. If you want to maximize the distance that they travel according to the angle that we throw it by. And so we can convert this parametric curve into a function y as a function of x. And how we can do so is we can rearrange equations 1.36 into the following equation such that we're inverting the function so that instead of x of t, we get t of x. So now it becomes, given a location x, you're going to tell me what time the object is at that location x. And we can actually only do this for functions that are invertible. What I mean by that is functions x of t is a graph that isn't monotonic, so it goes back like that, right? Then if I ask you at what time t is the value of the function this line, then there's actually three answers to your inverse function, and that cannot be, right? You can only invert this function x of t because this function x of t is a monotonic function. So for every x value, there's a unique t value that gives you the x. So invert this function to get t as a function of x instead of x as a function of t. Then we can substitute this t as a function of x back into y of t to give us equations 1.39. And equation 1.39 is y as a function of x. So if we plot this out now, we can see that y as a function of x looks something like that, describing the parabolic trajectory of the particle. And so what is this useful for? This is useful because if we find the x-intercept of this function, we get that one intercept is, of course, x equals to 0. right? But the other intercept is actually going to be equals to x equals to u squared over g sine of 2 theta. And we could have gotten this from the parametric curve as well. We could have gotten it from the equation that y of t is equals to 0, and then subsequently finding the t at which it hits the ground, and then substituting the t back into the function x. We could have gotten that also. We could have done it that way also. But this y as a function of x is actually more useful for other things. For example, if you want to find the envelope of the parabolic trajectory. And so now we see that if we have xn as a function of u, g, and t, then if I tell you that we fix u and we fix g, right, we fix the initial speed and we fix the gravitational acceleration g, but you can vary theta, then you can find the optimal theta to throw at such that the xn is maximized. In other words, you can find the optimal angle to throw the projectile such that the range of the projectile is maximized. So with that, right, that's projectile motion. So there are 3 very good questions over here, right? I'll invite you guys to try them. These 3 questions are very good, right? So we're talking about SJPO 2016 Q9, right? This question is actually best solved in, spoiler alert, the accelerating reference frame. The way to intuitively understand this question is to work in the reference frame of the fruit that's dropping. Right? In that case, we actually see that it's as if the object is just flying in a straight line towards the fruit. In the second question over here, this is a question that's quite good for understanding the region of reachability. One can prove that the region of reachability of an object is actually another parabola in itself, which is a slightly more advanced topic, right, but very interesting. And in this case, they ask us to find essentially the coefficients describing the region of reachability parabola. And this last question over here, it forces us to think about the relationship between some quantities, right? You can watch the detailed videos for them, but yeah, I think these 3 questions are very good questions which you should attempt. Okay, if not, that's all I have for this video. Thank you and have a nice day.